All right, so above one solar mass, all the way up to about four solar masses, you don't get any really quick movements. You don't really see this helium flash. You see, it's a more of a gradual thing. All right, so stars with 8 or more times. Okay, so this is when we start to see fusion beyond carbon. Just to let you know, like there is some fusion of heavier elements. In these stars less than 8 times the mass of the sun, but it's not significant. We're not seeing significant amounts. So this is when you start to see significant amounts of when you're at 8 times. So this is a star that has gone through its cycle. When it landed onto the main sequence, when it was on at stage 7, it was 8 times the mass of the sun. So once it starts to leave the main sequence as an 8 times the mass of the sun or greater star, those stars will begin to fuse in significant amounts elements heavier than carbon. Remember, carbon is element 6, right? So it's going to create a whole bunch of stuff on the first few rows, rows of the periodic table beyond carbon. That's where this stuff comes from, and to a much lesser extent, to these stars as well, and even stars as massive as the sun, right, will produce some nitrogen and oxygen. All right. Anyhow, notice what happens is, and we're going to see this in just a second. Its path across the HR diagram is essentially a straight line. It stays at just about the same luminosity. Okay, so that's what we called before, very similar to the horizontal branch. And so what'll happen is the luminosity stays the same, and here, let's look at this HR diagram there. So the luminosity will stay the same, and then let's go up here. The luminosity will stay more or less the same, and then it'll cool down. Right, it's cooling down because it's expanding. All right, so let's go back to where we were. But when you get to 8 times the mass of the sun, or more certainly, the star can die in what's called a supernova explosion. That is, we're going to see how that happens. Basically, all the elements, up to and including element 26, right? If you look on the periodic table, element 26 is iron, and so when a star fuses iron, so this is what we're seeing here. This is kind of a summary. I'll get into the iron thing in just a little bit. Basically, when you get to iron, the star doesn't gain any more energy. It doesn't. If you try, it could try to fuse the next element, which I think, if I remember correctly, is magnesium, but it won't. And what happens is the core will just almost instantaneously collapse in on itself. And during that time, after the core collapses during the supernova, explosion, that's when all the elements beyond iron are created. Again, it's not cut and dry like that. Like a star that's anywhere from 8 to 12 times the mass of the sun. It doesn't just stop at iron, right? It's creating heavier elements, but not in great. Well, actually, I'm sorry. It doesn't create a lot of heavier elements. It's certainly not in great abundance. So it's when it's more than 12 times actually. And this is theoretical. We don't exactly know at what point this happens. That's still ongoing research. But anyhow, this is what. So let's go over this table real quick because it's kind of nice. It just summarizes everything we've come to understand up to this point. So you're less than 0.01 times the mass of the sun. It's never going to become a star. That's what we call a brown dwarf, right? Anywhere from 0.08 to 1/4 the mass of the star. You're going to get a white dwarf that'll, eventually, die with just helium. Anywhere from 0.25 to 8 times the mass of the sun, you're going to get mostly carbon at the end, and that's a type of white dwarf that's the typical type of white dwarf that we find. And there is some, there's some carbon, nitrogen, and oxygen being produced. So those white dwarfs are those are the most common ones. Anywhere from 8 to, see now, when you get to 8 to 12 times the mass of the sun, you're looking at really rare instances, right? That doesn't happen all that much. And even more rare is when it's 12 times the mass of the sun. So those stars, 8 to 12, you're fusing, all the way up to neon, and there's large quantities of oxygen in those white dwarfs. And then when it's about 12 times the mass of the sun or more, and again, now you're talking about very rarefied stars. There's not a lot of them out there. I mean, but there are, obviously it's not hard to find them, but it's not the majority of stars. But those will explode as a supernova explosion, and we'll talk much more detailed about that in the next chapter, because that's kind of what the whole chapter is about. Oh, practically the whole chapter. So these things are still losing mass. It's not just from the So they're losing mass. It's not just from the supernova explosion, right, or any of these, helium flash or any of that, which does contribute to the loss of mass. But while these things are dying, there is solar wind carrying matter in the outer parts of the star out into space, right? And the basic idea is it's enriching the interstellar medium. And what I mean by enriching, there are heavier and heavier elements that you're going to find as time goes on in the interstellar medium. And where we are, 13.8 billion years since the Big Bang, when a modern star begins to form, there's a lot more metal in the interstellar medium, right? When our sun was formed 4.5 billion years ago, there was more metal and more metals, more heavier elements in the interstellar medium. Of course, now there's even more. That we're 4.5 billion years further along in stellar evolution in the Milky Way galaxy, and so there's going to be even more, more metals in stars that are forming now. All right, so let's see. This is a good example of the solar wind, and this is actual images from the Hubble Space Telescope looking at a red giant. Notice it's almost completely obscured, and then as time goes on, you're seeing the gas and dust blown out into interstellar space. Again, this envelope of material will eventually go so far away from the star, it becomes indistinguishable from the interstellar medium. That's the idea of enriching the interstellar medium. And then when new stars are born out of this, partially out of this material, and of course the hydrogen and helium that is coming, that originally came from the Big Bang, when that stuff forms, when the new stars form, that they have heavier material because that was created in the stars. The stars are factories of the periodic table. They create the elements heavier than hydrogen and helium in the that we find in the periodic table, all the way up to uranium. Nothing more than uranium. All right. Let's see, observations of stellar evolution in star clusters. Okay, so this is, again, this is the thing that I had mentioned a little bit, but we're going to explore this a little bit more. There was a lab, of course, about this, or there is if you haven't had this lab yet. This is the lab about stellar clusters. So clusters are born around the same time. All the stars in the cluster will be born at roughly the same time. And the the O and the B stars arrive on the main sequence first, and then the less massive stars will eventually arrive on the main sequence. But the thing is, the ones, the O and the B stars, leave the main sequence first, right? They're dead or starting to die after only about 10 million years or so. So some of them, a few 100 million years. But the further, so if you look at a cluster of stars and you see that some of the stars are still on the main sequence, but these really massive O and B stars have left the main sequence, that tells you what the age of the star cluster is. And the further down, so this is what's called, get my mouse again, this is called the cutoff point, right? So the further down the main sequence, so down means to the right and downward on the main sequence. The further down, the older the cluster. Right, so if these stars right here started to peel off the main, if the turn off point was right here, that would be a much older cluster. If the turn off point is way up here, that's a younger cluster. All right, yeah, they're just showing you the same thing. So if you found a cluster where any G, the turnoff point was down by a G-type star like our sun. Of course, our sun we expect to be around for 10 billion years. If the turnoff point was at the G-type stars, in other words, all the stars more than G, right? So these stars right here have left the main sequence. Then that tells you that is approximately a 100 billion year old cluster. Okay, let's see. So this is an example of a double cluster, Ch20 Persei. This is a relatively young cluster because we're only seeing the turnoff point up here with the B stars. And so you can figure out how old that cluster is. The Hyades cluster, which is another relatively young cluster, this is only about 600 million years old. That's kind of near. It's in the sky. It's in the roughly the same direction as the Seven Sisters, right? So anyhow, it's in the same constellation as the Pleiades. So. All right, so the globular clusters, so we're seeing their turnoff points are much closer to like a G-type star. So these things are anywhere from 10 to 12 billion years old. Let's see what else. Let's see, stellar evolution. Okay, so this is where things get a little bit different. And remember, you got over half the stars in the Milky Way have a companion, and it depends on how close the companion is. These binary systems, right? Two stars orbiting each other. So the closeness of the two stars really will affect the evolutionary path of the two stars. In fact, both stars. Not just the one that is left the main sequence. All right. So let me mention what this idea of the Roche lobe. Okay. So this a lot of times we talk about this more with planets and with moons. So if a moon if a moon is, so I know where these are stars here, but it's the same idea. If you have an object, okay, so a massive object, and you're within the Roche lobe, it basically breaks apart the spherical nature of an object, like a moon or something like that. If the moon is within the Roche lobe, it'll tear it apart. Tidal forces will tear that thing apart. All right, and so that's this idea of the Roche lobe. Okay, so of course Lagrange